We've been looking in this last chapter on rates of chemical reactions, talking about how fast product is produced or how fast reactants are used up. We talked about factors that affect the reaction rate. We talked about the effective temperature, temperature having two effects. Number one, of course, increasing number of collisions. Number two, increasing the percent of effective collisions, which meant those that could exceed the activation energy barrier. So again, if we were to look at a plot, energy over here increasing, and we start with a couple of reactants, A plus B, then we get something like this. Here's product C. This would be an exothermic process. This energy right here, over here, corresponds to EA, or the activation energy, meaning that particles that AB particles that collide, if they collide with that amount of energy, can become a product. All right? If they do not have that amount of energy, they will merely go back to being reactants. And what we said that temperature did was it increased the percentage of particles that when they collide are effective. The last thing we looked at as far as affecting reaction rate was concerned, we said, is there anything we can do to affect the activation energy? And the answer to that was yes. We can provide a catalyst. A catalyst provides a new pathway for the reaction to follow, in which case the new pathway has a lower activation energy than does the non-catalyzed reaction. And we demonstrated that in our drawing. Again, energy over here. And again, we start with A plus B. But this time we might find that we do something like this. We come over a couple of hills and then down to product, where the highest of these, in this particular case I've just shown the last one, but it would not necessarily be, that this activation energy now is much smaller than the activation energy that we had for the non-catalyzed reaction. And because of that then, at the same temperature, a greater number of particle collisions are effective. And so we have then increased the reaction rate by increasing the percent of effective collisions at the same temperature. And then we started talking about some types of catalysts as we were finishing up the last class period. And we said we could break the catalyst into two types: homogeneous or heterogeneous, or we sometimes refer to the homogeneous as active catalysts and the heterogeneous as contact catalyst. In other words, the catalyst acts as a surface area for a reaction to occur with a different pathway than it had without the catalyst. We looked at the active and contact catalyst in a chemical demonstration the other day, but also one of the major areas of active catalysts are the biochemical active catalysts, the enzymes. So we talked a little bit about enzymes. When we left off, we were talking specifically about contact catalysts and some of their application. Production of ammonia, the Haber process, we talked about it. We talked about the catalytic converter on the automobile. Again, a type of contact catalyst, lowers the activation energy barrier. And the last one that we mentioned as far as contact, we were talking about the use of contact catalysts in a process called hydrogenation. And hydrogenation is adding hydrogen to unsaturated organic molecules. So if we have a hydrocarbon that has a carbon-carbon double bond or triple bond in it, and we just used this as our simple example the other day. So we have something like this. It is possible to break that pair of electrons apart, that bond, and if we do that, then we will end up with something that would look like this. These hydrogens would be attached, and each of the carbons would have a single electron here. Now, if we take a molecule of hydrogen and break it apart, we will end up with two hydrogens, each with its own electron, and then one can attach here and one can attach there, and we end up then converting our molecule now to a C with the three H's on it, like such. So we have gone through a process called hydrogenation. And one of the major areas that we use hydrogenation is in food processing, where we want to change our polyunsaturated oils, corn oil, butter, peanut oil, things like that, to semi-solids, to use them more as a spread. And hydrogenation process is used then to add hydrogen to those molecules, making their molecular mass greater, and thus raising their melting point so that instead of being a liquid, they become a semi-solid. So that is one of the particular areas in the food industry. Hydrogenation is also used in the petroleum industry, where we're trying to modify. We may want a greater percent of saturated hydrocarbons in a fuel. And so by carrying out the petroleum through then a catalytic converter in the presence of hydrogen, we can get saturated hydrocarbons produced and increase our fuel value. One other place where recently, at least, contact catalysts have become important and utilized is in production of fireplaces. If you operate a fireplace, if you ever have one, or one of the wood-burning stoves, etc., you have a pretty inefficient system in terms of conversion of fuel to heat. And secondly is that we have a lot of air pollution when we burn a fireplace. And in areas, especially in the northwest and northeast part of the country, where fireplaces are very common and a lot of people burn, and even in the middle of the country, northern middle part of the United States, where people use a lot of fireplaces, the air pollution has become a problem. As a matter of fact, in some of the cities, they've gone to alternate burning days. So if you live in a particular area, or odd-numbered houses can burn their fireplace only on odd-numbered days. And people in even-number houses can burn theirs only on even-number days. Well, one of the ways to get around this problem is to produce then a catalyst which will aid the burning of the fuel from the wood. Corning has produced a catalytic converter that can be incorporated into the fireplace, and see its structure here. The catalytic combustor or converter is at the top of the burner box. This would be your normal burning. You have your regular grate and your wood in here burning. As the hot gases from this burning come up, instead of going straight up the chimney now, they're channeled through this catalytic converter. And as it goes through this catalytic converter, it undergoes further chemical change, going more to carbon dioxide and water, and releases additional heat energy. And so after it passes through this, then it finally goes back up through the chimney. This bypass damper is just so that you can control, of course, the temperature so that it doesn't get too hot in the burning process, or that this doesn't get too warm, so that you can bypass some if you need it. Also, you do have to get the catalytic converter hot before it becomes effective. So the first part you do a heating and then the catalyst takes over. But what is happening there is that many of the hydrocarbons, if you use a fireplace or a burning stove like this, one of the concerns is buildup of what we call creosote, which is an organic tar-like material. It's a hydrocarbon, builds up in the inside walls of pipes, which are colder. And then if you finally get a big enough layer of that and get the pipe a little too hot, you can set the creosote on fire and get a chimney fire, which of course can cause then a combustion of material around it. The pipe can get red hot and of course start a house fire. So anyway, in the process then, these hydrocarbons, instead of going up the chimney unburned or sticking on the side, are now going to be reacted with additional air, additional oxygen, and converted to water and carbon dioxide, and we get more heat out. Also, one of the other waste products of burning is carbon monoxide. And again, in the catalyst, if we take that carbon monoxide, react with oxygen, we get CO2, and that's an exothermic process, and we get heat produced again. So we make the burner much more efficient in terms of BTUs, which is the typical unit that we use for heating, a British thermal unit. We get additional BTUs for each piece of wood we burn, and we're decreasing the pollutants we put into the atmosphere. Now, I'm going to demonstrate this morning down here. This is a little sample catalytic converter. The catalyst part here, if you look right in here, this is the ceramic part that they're showing in the drawing then that goes up at the top part of the fireplace. This material right here, which is this then ceramic material. And what I'm going to show here is I'm going to have to get this heated up first, so we'll get this started. And while that's heating a little bit, I'm going to go ahead and I'm going to kill the lights so that we can actually see it. So it's going to be pretty dark in here. But you'll be able to see better what the catalytic converter is being able to do as we get going here. It's starting to heat up. We see it becoming red at the bottom. And once I get it heated up to red hot there, I think I've got it far enough now. I'm going to go ahead and turn off the flame for a minute. Now I'm going to turn it back on. You notice there's no flame anymore. You hear no burning, you hear the gas escaping, but notice that the catalytic converter is red hot. As a matter of fact, if I put my hand over the top, it's very warm. It's totally combusting now the propane without a flame at a much lower energy necessary condition than before. Again, and you see it's getting very hot. Whoops, got hot enough that it did ignite the gas this time. I had a little more flow rate than I probably needed. But again, you can hear the gas and burning without a flame. Now, you can buy these catalytic burners for like as additional little winter heaters, etc., that you can put out in sheds or area that you might be working outside in the winter and want a little additional heat. And it is a flameless process due to that catalyst being present. Now, normally for, of course, propane to burn, you do have to have a fairly high activation energy. That's why you have to have a flame. This has a little, what we call piezo electric starter in it, which is a crystal of quartz that when you squeeze the quartz crystal, produces an electric current that generates a spark. If you have one of these on a gas grill at home, you might have a little push button that starts your gas grill. For fireplace starters, they have little ones that you just have a little tank of propane or butane rather, and it has a little clicker on it, or like this. So it's merely a property of one type of solid. We talked about quartz earlier this year when we were talking about types of solid, diamond and quartz, silicon dioxide, and silicon dioxide crystals. If they're cut properly, actually when we squeeze them, we'll actually get an electron flow, and that's what operates as far as starting this. But it takes a fair amount of energy to normally burn propane and oxygen. But the catalytic converter lowers that activation energy barrier so that the burning process can go on without the needed flame, without that high of energy. And it is much cleaner burning. It is almost 100% efficient in burning as compared to normal burning process. So these are very, very effective as a catalyst. All right, well, I think that covers then what I wanted to say about catalytic converters. Anyone have any question on anything of that? One of the next things I want to just mention quickly here, and we have talked about it a little bit, and that is what we call the reaction mechanism, meaning how do we actually get from reactants to products. In most cases, when we look at a chemical equation, it's really not showing us what is happening. For instance, if I write 2H2 plus O2 yields 2 H2Os. Now that looks like a pretty straightforward, relatively simple chemical reaction. Kind of looks like two hydrogens collide with an oxygen and we produce 2 molecules of water. But in reality, this is a somewhat complex reaction system. And if we look at the overall reaction of this, stepwise, this is what we mean the mechanism. Actually, to go from hydrogen to water requires 6 individual chemical reactions. And each of those chemical reactions now has its own activation energy. So if we look at this graph over here, and this is an exothermic process, energy is given off in this reaction. It's an exothermic process. My film was kind of curling up there. Notice the difference here between our starting and our product. So this here corresponds to then the heat energy that we're going to get out of the reaction. But we notice that for each reaction there's an activation energy barrier. Well, obviously in this reaction mechanism, the first one here is the one that is the highest hill, the highest barrier. It's the one that's going to control the rate of the reaction. So the value of knowing a reaction mechanism is to know where to look to speed up the reaction rate. It wouldn't do us a whole lot of good to look at this third step and look for a catalyst for that step, because that step is relatively low in activation energy anyway. It wouldn't do us a whole lot of good to even do number 2 or 4. That's not going to affect the reaction very much. So the focus is to look where the highest energy barrier is and look for a way that we can catalytically affect that. Well, it turns out that, for instance, we can, by using a catalyst, in this first step, we can lower that activation energy barrier by probably 90%. If we were to take a piece of platinum metal, like a metal gauze, if we looked at the surface of the platinum, it would look like this. These would be the platinum atoms down here. And at that surface of the platinum atoms, if a hydrogen molecule approaches that, what happens is once the hydrogen sits down on the platinum, it actually, because of platinum's electrons in here, the hydrogen actually splits apart into two hydrogen atoms, each with its own electron. And that's the first step of the overall reaction process. That's this one right here. If we're doing it merely at normal, non-catalyzed, this requires several thousand degrees to actually get the hydrogen-hydrogen to break. Very high energy, very strong bond. When we do it with a catalyst, for instance, instead, we can actually carry this out at room temperature. For instance, I could take a tank of hydrogen and a tank of oxygen with just two needle valves so that I'm directing the hydrogen and oxygen together. And if I were to pass them through a platinum screen, they will combine. If I put hydrogen and oxygen together and want to get it to actually burn, I would have to heat it up to nearly 1,000 degrees to get it to heat non-catalyzed. So the purpose of knowing or studying reaction mechanisms as far as the chemist is concerned is to know where we should look. Where is the most effective way to affect the rate? Where is the highest barrier that we're going to encounter? All right? So reaction mechanism is the step fashion that we get from reactants to products. Most reactions are not as simple as the chemical equation looks. Chemical equation only gives us the stoichiometric relationship. It doesn't really tell us how the reactants become products. Okay? All right. In summation, then, as far as reactions, the things that affect the reaction rate, number of collisions. We talked about the collision theory. And so temperature and concentration. And we talked about both of these things affect the number of collisions. If we want more collisions, we can put in more reactants. If we want more collisions per unit of time, we can increase the temperature. So they're both directly related to the rate. The second thing then, in summation, was we talked about percent collisions exceeding the activation energy. In other words, the number of effective collisions, and that is dependent upon temperature, once again, and the catalyst. But there is a third factor that we haven't talked about yet, and that's this one here, and that's the percent that have the proper orientation. Now, this one is really pretty unimportant when we're talking about simple chemical reactions. If I talk about the rate of a reaction, let's say of something like a soda, that's not what I want, a silver ion, let's say reacting with a chloride ion in solution, aqueous, to form silver chloride, there isn't any orientation. I mean, we have a positive sphere and a negative sphere, and if they come in contact with each other, they can form silver chloride solid. It doesn't make any difference where they run into each other, so there's no orientation factor. But if we take a molecule, a more complex molecule, let's suppose that we were going to react something like pentene. 5 carbons, so it's pentane, and then we have a double bond up here, so it's pentene. And let's suppose that we wanted to react pentene with a chlorine molecule, and we want to put the chlorines on here, so we end up with the product now that looks like this, a chlorine and a chlorine, and then these others are hydrogens, these dashes. All right. Now, in order to get from the reactant to the product, then obviously this chlorine molecule needs to collide right here. If it collides over here, there's no reaction. If it collides in there, it's no reaction. If it collides here in the molecule, it's no reaction. It's only if the collision occurs at the site that has the carbon-carbon double bond do we have any probability of a reaction occurring. And so this is what we mean by then proper orientation, that when the collision occurs, it is colliding in the place where the chemical process could occur. So for simple reactions, orientation is not a major concern. For more complex molecules, orientation becomes a major concern. And one of the things that catalysts do is they help tie a molecule down. In other words, molecules in a gaseous state or even a liquid state are randomly moving around. They're tumbling, rolling, turning, and so at any instant only a certain number are oriented in one direction. But if we use a catalyst, a catalytic surface, then oftentimes we can get the molecule to stick to the surface and all of them become lined up. And if they're lined up, then the probability of getting a collision in the correct geometric spot greatly increases. So orientation does become important when we talk about more complex reactions. So again, in summation, the overall effect then of a reaction rate, of course, temperature and concentration for number of collisions, temperature and catalyst to change the percent effective, and then the number that happen to have percent proper orientation, which can be affected somewhat by a catalyst, then also affects the reaction rate. Okay. The last topic in the chapter deals with reaction of some organic compounds. And the particular organic compounds that we're going to look at reacting are alcohols reacting with organic acids, carboxylic acids as we defined them before. When we react an alcohol, remember this is the general structure for an alcohol. R is a hydrocarbon group. And this is the general structure for our organic acids. This is the acid group right here. And again, R can be any type of hydrocarbon on there, hydrocarbon group. If we react an alcohol and an acid in the presence of a dehydrating material, such as concentrated sulfuric acid, we will pull a molecule of water off from between these two. We can show doing this. We'll call it lasso chemistry here. We're going to go up here and we're going to now lasso out a water molecule. So we're going to say minus H2O. And when we pull that water molecule out from between these two, then R becomes attached to the O over here. And we end up with this particular new organic group called esters. That's the general functional group, the general group that we've talked about before as representing a class of organic compounds, R-O, C double bond O-R, that's an ester. Now, esters are very pleasant materials in many cases because they have nice aromas, they have fairly good taste. As a matter of fact, most of our pleasant smells in flowers, in fruits, etc., most of our pleasant flavorings, again, fruit tastes, certain types of candies, roots, etc., that have that type, like butterscotch, are esters in nature. Let's look at just a few examples here. Here are some esters and some of their corresponding, their common names and also the fruit that we find them in. Now the first part of the name here is the alcohol. So we see C5H11, that is really pentanol, in other words the 5 carbon alcohol. And from the 5 carbon alcohol we took off an OH, and then we've got this group right here, which is the acid, and we lost a hydrogen from it. And that acid, the 2-carbon acid, the common name for the 2-carbon acid is acetic acid. And the common way of naming it is to call the alcohol pentol. From the pentane, we just add the YL as an attached R group. So this is R over here. And then the name of the acid was acetic acid. We dropped the IC and changed to the ATE. So pentol acetate is the fairly common naming system. And if you look at artificial flavorings and that in the grocery store, you'll see them listed in this fashion. Now the IUPAC name would be to name it in a different fashion, but this is the most common, so we'll just look at this particular way. Well, this is banana. So if we take the 5 carbon alcohol and react it with vinegar, essentially acetic acid, we put them together to make this ester pentyl acetate, which gives us the banana flavoring. Or we look at the next one here. Here's ethyl, that means the ethyl alcohol, our grain alcohol, coupled together with bute, which stands for 4, so this is a 4-carbon acid, butyric acid. As a matter of fact, butyric acid is the organic acid, and I think I may have mentioned this earlier in the year, but butyric acid is the acid that we get when butter becomes spoiled. As it becomes oxidized, the butter then is converted to butyric acid, and the butyric acid has a very rotten, pungent odor. If you've ever smelled rotten butter, it is not pleasant. And here we take this rather obnoxious smelling material and combine it with ethyl alcohol and make a very nice then flavoring, which is pineapple. And we see some more. Here's apricot, orange. Let's go down here. Here is rum. Ethyl, that means again, ethyl alcohol. This time we're taking the 1-carbon acid, and the 1-carbon acid is formic acid. That's its common name, methanoic acid, formic acid. And if we combine these two, we make ethyl formate, which is the rum flavoring. So we see that the esters as a group are very pleasant and useful from a commercial standpoint for producing artificial flavorings. Now, just using one, for instance, if we took methyl butyrate, yes, it will smell a little bit like an apple, and it will taste a little bit like an apple, but it won't taste totally like a real apple, because most fruits are a combination of 10, sometimes as many as 20 or 30 different organic chemicals that add to this major component as far as producing the overall flavor. So just having one does give us the essence of the flavoring, but doesn't give us necessarily the true fruit flavor. Okay? Now, we talked about, when we were talking about alcohols and acids, we talked about the fact that you can have 2 alcohols in a molecule. We called it a diol. You can have more than one acid group in a molecule. Dicarboxylic acid, as a matter of fact, one that we specifically had talked about was oxalic acid, which is 2 carbons, and both ends are organic acid groups. Oxalic acid. If we take now these and put together, again by dehydrating, we're going to pull a molecule of water out and we're going to put these two together. But the key thing to notice is that even after we've put them together, we still have now an alcohol group over here, and we still have an acid group over here. So, whoops, so we still have an alcohol that could react with another acid, and we have an acid that could react with another alcohol. So let me just put this together, and I'm just going to put everything in here now as an R. That's the whole mess. That's the actual ester part at this point. But we still have sitting over here, as I say, this acid, and on this side we still have over here an alcohol. So if another one of these were to come along, then if we brought along another one of these, HO-R-C double bond O-OH, so we form 2 of them, and now we again loop off another molecule of water here, like that, and we're going to form another ester bond. But when we got done doing this one, notice we've now taken the water off. Notice what do we have? We have an acid end over here and an alcohol end over here. This end could react with another acid. This end could react with another alcohol. And so we begin hooking these together. This can go on and on and on. If we have a dialcohol molecule with a diacid molecule and put them together, they can hook together and then hook together and hook together and hook together and hook together and hook together. And what is the prefix we use for many? Poly. And so we have a chemical called polyester. Anybody ever hear of polyester? Well, polyester has been used for many years as a fiber to make clothing, polyesters. Matter of fact, polyesters became very, very popular as a clothing material because you could originally press it and it became a permanent pressed material. It kept its shape. And so you could take it and throw it in the wash machine, throw it in the dryer and pull it out, and it looked like it was nice and pressed. Had a permanent press on the pants, and the shirts were fine. They weren't wrinkled. And so it had a big attractive from the standpoint of not needing ironing. Now, one of the drawbacks of polyesters were that they don't breathe very well. And if they don't breathe very well, it means then that they trap heat and moisture in. So it's difficult to evaporate your perspiration in the process. That was a negative aspect of polyesters. But they were very popular through the 70s and even into the early 80s, and now we've kind of switched back to more natural fibers once again. We've gone back to cotton. And cotton, of course, you do have to iron or you have a terrible wrinkled mess when it comes out of the dryer. And so that's been a disadvantage, but it's a cooler, it's a more breathing material than polyesters. But the chemist isn't daunted. They've gone back to the drawing board, and they've now figured out a way of remaking these polyesters into a different branched type of structure, which have greater breathability. And I think that you will see within the next 5 to 10 years that certainly mixtures, if not 100% polyester, is going to come back into clothing once again. And primarily again because of the advantage of not requiring ironing, so that materials look pressed and neat when you take them out of the dryer. All right, the polyesters. We talked about 2 other organic materials. Well, one other, I should say, the amine And the general formula for the amine was an R group with a nitrogen and a couple of hydrogens on it. That's an amine. And if we take an amine and we combine it with an acid, so the only difference here is we're using an amine instead of an alcohol, but we're still using an organic acid. And again, we're going to use a dehydrator, concentrated sulfuric acid. We're going to lasso out a molecule of water. So we'll say minus H2O here. And we're going to hook this nitrogen then to this carbon over here. And so when we do that, we get this structure right here. Now, the R, which is some hydrocarbon group, the nitrogen there hooked directly to this carbon, double bond oxygen and an R, and this new molecule here is called as a group. We had the esters when we used the alcohol. These are called amides. That's an amide bond. As a matter of fact, this is an important bonding technique or process when we begin looking at biochemical reactions, especially when we look at protein structure in Chapter 14 on biochemistry. We'll come back and talk about this amide bond once again. Okay? Now, again, if we use a compound which has two amines in it, a diamine, and use a dicarboxylic acid, not only can we get this to occur once to make one, we can continue the process out. So we can hook them together and together and together and make giant molecules once again, which we call polymers. And then specifically in this case, we refer to them as polyamides. One of the most common polyamide is that which is referred to as nylon. There are many different types of nylon because you can use many different acids and you can use many different amines, and so you can produce different types of nylon. But nylon is a synthetic material made from an amine and an organic acid. And then the fiber of nylon, of course, can be then spun, wove into clothing, into fibers, etc., into fabric. Nylon was discovered and actually produced before World War II, but in World War II, where we needed the nylon to make parachutes for the armed forces, then nylon became very scarce as far as for the women to purchase nylons for wearing on their legs. And so nylons became rationed during World War II as the nylon had to be used to, as I say, produce parachutes and other materials, rope, etc., necessary for the war process. Shortly after World War II finished, then of course the reproduction or the rechanneling of the nylon now back into, again, use as far as producing nylon stockings, that type of thing took place, and of course it became available, and the picture in the text shows a sign being hoisted up again about nylons being for sale, and this occurred shortly after the end of World War II. All right, so we have two different types of polymers here that we've looked at this morning. Polymers, okay, and actually the mer stands for individual units. That's, if we talk about a monomer, that's one unit. Mono meaning one. Polymer means that we've taken these units, this amide, and we've done it over and over, hooking them together to make then a polyamide or a polyester material. All right. Any questions on any of those processes? Okay. As we go on and look a little bit further at chemical reactions, we're going to again look at rates, but we're going to now need to consider another factor in our overall process. Let's suppose that once again I were to take, as we looked at the beginning of chapter 11, let's suppose I were to take a container and I put in some A particles and some B particles, and they react to form the product C. Initially, when we start the process, the only thing we can have are, of course, A particles reacting with B particles. Now, when an A runs into an A, nothing can happen, so that's a collision, but it's not an effective collision as far as the reaction. But if an A runs into a B with sufficient energy, then it could produce C. And we would say that the rate of the reaction is equal to or proportional to, it's dependent upon, I guess we would say, is dependent upon the concentration of A and the concentration of B. In other words, if we have more A and B particles in there at a constant temperature, the rate of the reaction is going to be faster. But after some length of time, after this process has been going on for a while, we're going to start getting some C particles in here. And the question then becomes, what happens if two C particles collide with each other? Well, actually the answer is that we can get what we call then a reverse reaction, where the C collides and gives us back A plus B. The reverse reaction is occurring. If we have enough energy in the system for A and B to get over the hill to become C, then we have enough energy in the system that if two C's collide properly, they might have enough energy to get over the hill to go back to being A plus B. And so we have then a reverse rate, and that rate is now proportional, again, to the concentration of C in this case, because C is the reactant for the reverse rate. Well, overall then, we can look at the equation in the following manner. We can say A plus B yields C, and we call this the forward reaction. And the way I've drawn it here is that we're talking about it as an exothermic process. And we have a reverse reaction, so this is called, that should be an R there, it doesn't, well, it's a little R there, RR, rate reverse. And rate reverse, of course, is going to then depend upon the concentration of C. And so as we continue on at our look at reactions then, we'll talk about now the reversible process, and a process called chemical equilibrium as we move into chapter 12 on chemical reaction rates.